Okay, ladies and gentlemen, our next speaker hardly needs any introduction. So Professor Gianni Royer-Carfagni from the University of Parma will present his work. He is also a professor at the University of Houston in the United States. Apart from that, he is also very active in standardization, both at national level in Italy, but also at international level, more specifically in the TC250, in the subcommittee 11, where the ongoing work for the future Eurocode on the design of glass structures is taking place. And yeah, he's also a licensed professional engineer. And his topic of today will continue a little bit on the thermal performance, not of vacuum glass, but of insulated glass. So Gianni, the floor is yours.
Thank you. Thank you very much. Yeah. So the title of my presentation is Innovative Finite Element Method for the Thermal Analysis of Architectural Glazing Exposed to Solar Radiation. And I will present a proposal for a simplified engineering approach to this problem. The first author is Professor Laura Galuppi, who gave a definite contribution for this work. This research was supported by Maffei Engineering. You can find Massimo Maffei as a co-author, who is the president of Maffei Engineering, and Ali Haidar, who is a PhD student at the University of Parma, supported by Maffei Engineering. So the problem is that of architectural glazing, which is exposed to solar radiation. What you can find is essentially that there may be an uneven distribution of temperature due to, for example, cast shadows, which are induced by neighboring buildings, by trees, by sunshades, by fins, and whatever. So this is an important problem because the uneven temperature distribution in the glazing may produce a thermal stress. And my personal experience in Italy is this breakage, glass breakage due to the thermal stress is one of the most important causes of failure. And there are there have been a few problems. And the problem is that this is due to the uneven temperature distribution. It is not, the unique parameter is not the temperature difference. For example, if you have a temperature which varies linearly in space, this satisfies the Saint-Venant, the thermal strain satisfies the Saint-Venant compatibility conditions, so the thermal stress is zero, whatever the temperature difference. You have to take into account what is the distribution of temperature in order to find out the thermal stress. And the key parameter is to assess the temperature distribution in space. And this distribution of temperature, of course, you have some parts that try to expand, some other part which tries to contract, and this is the reason why you have the development of the thermal stress. And this is very different from a problem in which you want to assess what is the thermal performance in terms, for example, of insulation, because you want to calculate the temperature distribution to find out what is the thermal stress. This is a thermoelastic problem. So the thermal problem, you have a paradigmatic case. I will discuss only about monolithic glass. We have a pane which is exposed to solar radiation, which is partially irradiated by a contouring frame. And you can recognize basically four regions in a standard paradigmatic problem. You have a region one where the glass is directly invested by the solar radiation. You have this region two in which you have shadows. And for example, just a percentage of the solar energy hits that part. According to a French standard, you can say that 10% of that invest the part. Then you have a region 3, where the glass is trapped in the window frame, but region 3 is in contact with region 1. And region 4, which is still trapped in the window frame, but it is in contact with region 2. And this, I think, that's the minimum classification of the regions to obtain reasonable results. Now, another thing is that the thermal problem is usually associated in differential form. It is usually associated to a differential equation of a parabolic type, in which you can see you have a second derivative in space. And this may produce some problems because if you want to use a finite difference, you have to consider to have to approximate the second derivative. You can do that, but if you are interested in sharp temperature variation, and this is what you are interested in if you want to calculate the thermal stress, you may have some problems in using finite difference. Apart from that, you have, of course, to consider what are the boundary conditions at the various surfaces. You have a term which depends on convection and a term which depends on radiation. The terms that depends on radiation is dictated by the fourth power of the temperature, but a thing that is usually done is to make a linearization of this boundary condition in a neighborhood of the average temperature, so that also the boundary condition in terms of radiation can be expressed in terms of the difference, the linear difference between the various temperatures. Now, the differential form of the heat conduction equation involves the calculation of derivative, which are difficult to do. And especially if you have to calculate the temperature gradients, it's not easy from a numerical point of view. There is a very ingenious approach which was proposed by Maurice Biot. Maurice Biot was a Belgian engineer. Then he moved to the United States and did his graduate study at Caltech under the supervision of Theodore von Karman. And he proposed a variational approach to the thermal conduction equation, in which the variable is not the temperature, but it is another field which we called the heat displacement field, which is referred to with the letter H here. And you can see that the temperature is associated with a divergence of H. This means that the heat displacement field enjoys a much better regularity with respect to the temperature because, roughly speaking, it is the primitive function of the temperature. So you can consider a nice problem in which you may have a very strong temperature gradient in a variational form, but just introducing this kind of variable. And this kind of variable can be, of course, it is in variational form, so it can be readily implemented in a finite element code. And here I represent a few examples in which we consider shape function for the heat displacement field, shape function which of course can consider the three-dimensional problem, because if you make a one-dimensional problem, you are not doing anything if you are interested in assessing what is the stress, the thermal stress in your glass. So we have different shape function for what concerns the in-plane variation of the heat displacement field and the out-of-plane variation, because the finite element allows to do you to select what are the most suitable shape function for your numerical calculation. And what you end up, for the discretized form of this equation, you can see on the right-hand side, it's the solution of a multi-degree of freedom of oscillation in which the mass is equal to 0. So you have only the elastic term and the damping term. And this is, of course, because of the governing equations of the parabolic type, and they are not of a hyperbolic type. So this is just one example in which we consider a simple case in which you have region 1 and region 2. The finite element mesh is represented at the bottom. And this is a 2D problem, basically. So we used it as a benchmark problem because it is not 3D, it is 2D, basically. So you can implement also quite easily the differential form of the equation. And we have found that we have an excellent agreement with the results for the differential form of the problem, that is the standard one, with difference less than 0.04 degrees Celsius at the steady state. But of course, the program it's much more efficient from the point of view of computational time. This is another important thing, because apart from doing a finite element implementation, which takes into account what are the basic characteristic of a problem, you like to conceive an engineering approach for everyday calculation. And an important thing is to consider what is the distribution of a temperature. Here you can find the distribution of a temperature, the y-axis, the vertical axis in these two graphs, and in the abscissa you have the y direction. You can see that the temperature is mostly uniform in these regions, apart from the transition from the hot part to the warm part, from the hot to the cold part, and this transition zone is indicated by the steep descent. You can see that the width of this zone is approximately 10 times the thickness of a pane. This is a very important remark that can be used because the temperature is almost uniform in the region apart from the transition zone. So in a simplified engineering approach, we call it a CEA, the C. In the C, we again classify the four regions of the pane, and we suppose that the temperature is uniform in each region. So instead of having to solve a differential problem, you just have to solve an ordinary system of four equations, because the unknowns becomes only the temperatures in the four regions. So you have only four unknowns. The calculation in the simplified, in the C, in the simplified in the engineering approach is very straightforward, because you have just to do an energetic balance. So you just say that the thermal energy which is stored in a region is equal to the heat flowing into the region minus the heat which is flowing out of the region. And here are the various contributions which correspond to the absorption of solar radiation, to heat convection, heat radiation by external internal surfaces, and heat conduction. The term heat conduction, which is most of the time neglected in current standard, is one of the most important if you want to assess, if you want to have a good estimate of the temperature distribution. Neglecting heat conduction usually provides a very drastic overestimation of the temperatures in the various regions. So the various terms are analogous to the previous one. You have, of course, the absorption of solar radiation, in which you consider that, for example, region 3 and 4 have no absorption because they are shielded by the frame. Region 2 receive, for example, 10% of the solar radiation. Region 1 receive 100%. Then you have a heat convection between glass, the heat exchange due to the air flowing inside and outside. Then you have the solar, the radiation from the sky vault and other surfaces. And then you have also the other contribution. And for what concerns the heat conduction, you use the result from the previous calculation, with the previous numerical calculation, and you assume that you have that the region in which heat conduction takes place is a thin strip. But you take into account that the thickness of the strip is about 10 times the thickness by this coefficient beta that you can find in these formulas that you take equal to 10. And finally, you have the heat storage in the various regions. So what you find out, it's a very simple governing equation. And you have a system of 4 equation which is algebraic in space and differential in time. And from these, you can determine the temperatures in the 4 regions. So this is just an example. You have as input datum, which is the solar radiation as a function of time. And you have also the time-dependent external temperature here. And you can calculate, for example, what is from the variational, from the finite element method using BO variational approach, which is called BVM FEM, which is a acronym from BO variational method, finite element method. You can calculate what is the temperature on the inner surface, the front surface, on the back surface, and also the mean temperature. The mean temperature is the only one that the CEA approach can calculate. And for this case, you can see what is the transient problem. And of course, the CEA, the C, cannot provide you a very complete scenario, but it is very good for finding out what is the average temperature in the thickness, because you can see that you have, despite its simplicity, you can find what is the average temperature in the thickness for the 2 regions with an error which is less than 0.5 degrees for region 1 and 0.3 degrees for region 2. Another example is more complicated because you have a shadow region which is like that. And the shadows are very, very, you have to be very careful because they can produce a very high thermal stress in your glass just because of the elasticity problem. You may have a stress concentration. And for this monolithic plane, again, you can find for this case an approximation, which is an error of 0.0 degrees in region 1 and 0.0 degrees in region 2 for what concerns the average temperature in the thickness. But the agreement is really excellent from our point of view. This is a more difficult problem in which you have the other 2 regions, but you have also regions which are shielded in the frame. And you can see from there that it is important to consider region 3, region 4, if you have a conduction, because region 3 is in contact with a hot region, and region 4 is in contact with a cooler region. And these are the results. Again, you can find a very good agreement if you consider the temperature at a point in the middle of the various regions. And you have errors of the order of 0.5 degrees and 0.2 degrees and 0.3 degrees for regions 1, 2, and 4. In any case, the result is that you can have a very nice approximation. The various standards take into account various forms. Actually, there is a little bit of confusion because many standards also give conflicting rules. But in any case, what we can see is that in general, what standards tend to neglect is the conduction. Instead, if you want to produce a reasonable estimate of a temperature, you have to consider the heat conduction through the various regions. Otherwise, you make an estimate which is too much on the safe side, and this may produce problems in the design. In the proposed method that I just presented, we consider all the heat exchange contribution. So what we have done, we have tried to present a finite element code which is specifically conceived to determine the thermal stress. It relies on Biot variational principle. The code is very efficient. And from the resulting paradigmatic cases, we have proposed to a simplified engineering approach in which the solution is the solution of a system of algebraic equation in space. And so you have much more simplification in that. It relies on the observation that the conduction between the various parts takes place in thin strips. And from these, we have found that the temperature difference with the finite element calculation are very, very, very small. So the simplified model is efficient. Of course, I'll just show you the simplest calculation for a monolithic glass, but we have already what is the extension to multi-laminate glass and insulating glass units. It's already been published, actually. And then this is a list of papers that just report with more details what I have talked about today. And now the problem is how to calculate, to make the safety verification of glass. And in this case, you need to calculate what are the consequences of breakage, because you can accept, for example, a higher probability if the consequence of breakage is very mild. So some work is still needed to find out what is a suitable verification formula. But in any case, I finish with a joke that a broken glass is like a broken heart. It always brings sadness, but also live surprises. So thank you very much.